Okay, so welcome back everyone. For you made it to the last day, so hopefully you're not too scared of the topics that we've been talking about. Today I'll tell you a little bit about something. Again, connections of eigenvalues to other problems. I'll pick up where we left it yesterday. So yesterday we talked about something about sign adjacency matrices. I said something they're equivalent to two covers of graphs. So sign adjacent, I'll start today a bit different than I did yesterday. I'll start from sign adjacency matrices, which I define informally, but you can define formally as follows. So we have, as always, a graph gamma with adjacency matrix A, and now assigning, or you can say an edge signing, if you want to be more precise, of gamma is a function, just a function s from the edges to +1 and -1. Okay, that assigns to each edge a value of +1 or -1. That's all it is. And then the sign adjacency matrix associated, let's call it A subscript S, associated with S is the V times V matrix whose entries are defined as follows. So in the position xy, you put the signing of the edge xy, S of xy. Let me just put S of xy. If x is adjacent to y, or xy is an edge, and you put 0 otherwise. So informally, as we mentioned, well, you know, if you want to say it in words, AS is obtained from A by changing some, but possibly none, so some +1 entries to -1, so that the matrix is symmetric. So the matrix has to stay symmetric. So when you change the +1s above the diagonal and below the diagonal, so the transpose, such that the resulting matrix So yesterday we saw two places where this matrix appears. So yesterday we saw in Huang's proof of sensitivity conjecture, he does sign adjacency matrices of the cubes of the Qn. I'll tell you in a little bit something about this after we discuss the connection with again recap the connection with 2-cover, that this sign adjacency matrix and the 2-cover associated with it was actually studied by people in the 80s, but in a different context. They just didn't look at this question. So now, so this is a sign adjacency matrix, and now let's go to the cover. So we did this example yesterday. We had the K3. I think we drew it like that. You have A, B, and C. So the usual adjacency matrix will be A, B, C, A, B, C. So you have ones everywhere except on the main diagonal. And now, so let's do this backwards than how we, kind of how we did it yesterday. Let's come up with let's take a signing. So for some pick a signing S of gamma, and write down the, the sign adjacency matrix. So we did something yesterday, maybe we're gonna go crazy today and do something else. So let's try something else. So let's try here, -1, -1, -1, -1, 0, 0. If yes, questions?
Does it go 0?
Oh, sorry, yeah, thank you. I meant to say -1. Here, let's put some 1, let's keep some 1s. Yeah, thank you. So this is a sign adjacency matrix. And so from this sign adjacency matrix, what we'll get is we will get the 2 cover of gamma by the recipe that we did yesterday. So for each vertex here, you make 2 copies. So let's say A0, A1, B0, B1, and then you make here another copy, C0, C1. And now you look for each edge and you see what the sign is. So let's look, so ABC, so let's put here ABC, ABC. So A and B is a -1, so it means this edge AB, I will do the crossing the diagonal, so I'll do this. Okay, so this is because the sign of AB is -1. Of the edge AB is -1. And then I won't write for each of them, but AC, you will do the same. So AC, you will also cross like this. And then, what is the last one? BC, you keep them parallel. Okay? So that's. And yesterday we proved this, this proposition. So I won't define here the 2 cover, but I will just say here, let S be a signing of gamma, denote by gamma prime the 2 cover associated to S. So this would be the 2 cover that I associate to S. And yesterday we proved that the spectrum of the adjacency matrix of gamma prime is the union of, I'll put it here, the spectrum of A and the spectrum of AS. So we did this yesterday afternoon. Now what happens, you see, no matter what signing you have, these eigenvalues remain in the big graph, and these are usually like the eigenvalues from here. These are usually called the old eigenvalues. I mean, old. Yeah, it's just they're always there. Okay, doesn't mean sometimes young people talk old and it has maybe a negative tone, but there's nothing negative here. It's just they're always there. Okay, these eigenvalues are always there. So these are called the new eigenvalues. Okay. Okay, so now I'll tell you another context in which this 2 cover appears, and this was done way before Huang's work, but in a different context. Okay, so I will just give you one more thing about to cover, then I'll change gears and tell you something about expansion constant of graphs and expanders and all that. So I'll erase here. Okay. So what observation I want to tell you is something very simple, and it will be also again another exercise number. Okay. So here's the idea. Here, what did we see? This graph is too regular. What happens to the two cover? Too regular. For each vertex, you get two copies. But each of these copies has the same degree as this vertex. Because A is adjacent to B and C, A0 is going to be adjacent to B something, can be 0 or 1, but is also adjacent by C something. This is this condition that if you pick a vertex and its neighborhood, you will have a bijection. There's a bijection between them, okay? So the same thing happens everywhere. So what you expect is that, so this is a proposition. Your colleague says it's exercise 32. If gamma is a, let's say, deregular graph, then any two cover of it is a deregular graph. Because the degrees are preserved by this procedure. So, and yeah, try to do some examples. I asked you yesterday, try to play around, for example, try to show that the cube, the three-dimensional cube, is a two cover of the complete graph K4. That's an exercise, and so on. Okay. Okay. So before we go to expanders, here's what can happen here. You can if I want to construct, somebody asks you, says, okay, pick your favorite D. Okay, D equals 3, and they say, can you give me an infinite family of three regular graphs? So what you can do is you can say, okay, here's my first three regular graph, K4. Then I take a two cover of it, pick one. You get another three regular. What? Yeah, you get a, yeah, but here if you get a three regular graph on how many vertices? On 8, because yeah, so this is on 8 vertices, and you keep going like this, you get on 16, three regular. So you can do this in exponentially many ways, because each graph has 2 to the power number of edges, 2 covers, because you can change every edge, okay? So now we'll see a little bit later, people will be interested in actually picking up from this large collection. You will want to find some graphs that have a certain property. So that's where we're going with this. But again, this is an easy recipe to construct regular graphs as much as you want. Okay.
Is there any relation within the spectrum of A and As, depending on the sign?
In general, well, I mean, in general, I don't think there's any. I mean, you know, there are two obvious signings for which you know exactly what happens. If you sign everything with 1, then AS is the adjacency matrix itself, so you know what happens. And if you sign everything with -1, then it's the negative of the adjacency matrix, and you also know what happens. And after that, as far as I know, you don't have like for general graphs, you don't have a clear, so that is where the game is played for these problems. We'll see it's about this signing thing. How can I signing such that something happens? So people have studied a lot of these problems. Because again, it's equivalent to this to cover. What signing should I do such that my to cover has this property and so on? So this is a very good question, but yeah. So yeah, I don't know of anything in general. We'll see a little bit. So I'll talk a bit later about distance regular graphs, and you'll see another example of. I don't know if you're familiar with the dodecahedron. You'll see, like, I'll tell you a little bit about dodecahedron and Peterson graph. There's something there as well, but in general, we don't know. Okay. Okay, so let me tell you now about something, the expansion constant of a graph. So, definition. Again, as always, let gamma be a connected graph, so I want it connected. The expansion constant, people usually denote it by h of gamma, or sometimes it's called the edge expansion constant, but I'll just call it expansion constant of gamma, is defined as follows. H of gamma is the minimum of the following quantities: the number of edges between S and V minus S. But now, that was the thing we did when we talked about edge connectivity, but you normalize this. You divide by the cardinality of S. And this is over all S subset of V with cardinality of S at most half than the number of vertices in V. Okay, so if you're given a graph, okay, I'll give you some examples here. Our friend let's do also the cycle. Let's do also and so on. And let's do one more. Oh, the other way. Okay, when you look at this definition, okay, it's the minimum over all subsets of cardinality at most V. So if V has n vertices, how many, roughly speaking, let's say n is even. How many subsets you're going to have that have cardinality at most a half? How much? Yeah, in total you have 2 to the n. This one will be probably half of it because they're in bijection with the other ones that are bigger. So here, if you're looking at these subsets, it's probably something like 2 to the n minus 1 or something. So it's exponentially many. Okay. Now, if you have time to spare, 24 hours on a train. I'm sorry. I won't say who is spending 24 hours on a train. You can check all of them, But even for here, n is 10, you have, yeah, don't do this, okay? You have other things to do. So let's do some examples for these graphs. Again, I'm trying to convince you that this parameter will be, in general, difficult to deal with. So pick a graph here, any graph, and then let's try to figure out this constant. Okay, the easiest, let's take complete graph. Complete graph, in complete graph, Kn, if you give me a subset of vertices, this is V minus S, let's say cardinality of S is M, this is N minus M, and let's say M is less than or equal than N over 2. So here, I'm counting, what is E of S V minus S? This is not a trick question. All the edges are there, because it's a complete graph. So this is M times N minus M. Nothing complicated. And then the number of edges between S and V minus S divided by cardinality of S will be this divided by M, so it's N minus M. And now what do we want to do? We want to minimize this thing. So you want to minimize N minus M. So H of Kn, what is it going to be? It will be something like if N is even, you can go all the way to the half. So you'll get N over 2 if N is even. But if N is odd, M can go at most to N minus 1 over 2. So this becomes N plus 1 over 2. I mean, I could have written it also as floor of ceiling of N over 2. Like it's the same thing. Okay, so I try to convince you this is difficult, but then I show you this. It's easy. Okay, so this one is done. Pick a graph, any graph. This is like a magic show. Pick. Which one? Cycle. Okay. So, okay, I trick you. This is bait and switch. I gave you C5 at the beginning, but now I'm gonna ask you about bigger cycles. So we're gonna talk about Cn. Okay. So again, at least you see here H of gamma is a minimum. So if you give me some S that you think it works, we can get an upper bound for H of it, okay? Because it's a minimum of all these things. So give me some S that would work in this case. Let's say N is even, like in the picture. So somebody says alternating, but alternating will have many edges because you want, what do you want? You want to minimize this. So what you like here is you like the S to be big, and you like the number of edges between the parts to be small. So you can cut, for example, you can cut it to half like this. You can take the half of them, and if S is like this, then what do you get? So this is for cycle. What we get is less than or equal, it will be two edges, because you have two edges here, just these two edges. And let's say in general, I can do it something like this. It will be probably floor of N over 2. That's the smallest part, okay? And this is roughly speaking 4 over N. Again, it depends on even or odd, okay? And exercise 33, try to figure out that this is actually, so the expansion thing of the cycle actually equals, so if 4 over N, if N is even, and if N is odd, you see what you put here. You put 4 over, I think, N minus 1 if N is odd. So, I mean, as expected, you see a big difference. So here, graph Kn is very connected. You get very large expansion, because this one, I didn't say it, but what it measures? It measures how hard it is to break the graph into two parts, that the parts are large, relatively large. Like, if I didn't put this S here, I could just get away with edge connectivity. That's edge connectivity. But when you put this S here, you kind of want the parts to be large. That's the idea. Okay, because for example, yeah, this is actually a good thing to notice. Like here, for example, what would be the edge connectivity? The edge connectivity is 2. And there are many ways you can carry with 2. I could carry with 2, I could have carried with 2 here, delete 2 edges. But if I carry with 2 here, for this problem of expansion constant, what value I get? I get 2 edges divided by the smaller part, which is 1. So here you want these sizes of S in which you break to be relatively large, so that that will give you the minimum. Okay. So, okay, so these are kind of the opposite ends of the spectrum. The complete graph will be the one that is the most connected, and you'll get the higher for n vertices. This will be the largest expansion constant. This one, as you see, if n gets large, this vanishes pretty much. And this will be important in a little bit. I mean, again, for Kn, it's clear. For Cn, you require a little bit of proof, because what I gave you here, it's an upper bound, so you have to actually argue that you cannot do any less than that. Yeah. Okay, so we did this, we kind of did this. Which one do you want to pick next?
Peterson.
Peterson. So what do you think? Okay, H, Peterson. Again, we're going for upper bounds. So upper bounds is pick a subset where you see like few edges coming out, and see what number you get when you do this calculation. So I could pick, if I was doing edge connectivity, I could pick this vertex. There are 3 edges coming out, but I divide 3 by the smaller size, and the smaller size is only 1, so I get a 3. But now you're looking for bigger subsets. So you usually you look at the cycle on the outside, and you will have 5 edges connecting it with the outside, so you'll have 5 over 5 is 1. Okay, so the expansion constant of this, because, so this is, you can take either this is a set S or the complement of it is a set S. To make the drawing easier, I'll take this S. So what you have is at most the number of edges between, let me do it like this, between this and between this, divided by the cardinality of here. It's not very formal, but okay, you get the picture, okay? And this is, you have 5 here and you have 5 here, so you have 1. Makes sense? Can you do any better? It's a little bit harder here because it's not quite, I mean, even for cycle, you haven't done it yet. I haven't checked your work to see if it's correct, but you see things get a little bit more, how would you prove that this is greater or equal to 1? If let's say you want to prove that this is 1. Here you see, you will have, maybe this one you have time to do because it's only 2 to the 9, not to the 10. So it's only 500 cases. And you still have room on your notepad. So, okay. But I'll show you in a little bit how you can use eigenvalues to actually prove that this is going to be 1. That's the key. And then what about this one? H of Q3. Again, if I want an upper bound, what should I yeah, I can take one of this, and is at most 1. And this is the actual upper bound for any n-dimensional cube, because remember, for n-dimensional cube, there were 2 copies of the n-1 dimensional cube joined by a perfect matching. So if you take that partition, you will get an upper bound of 1 for every n-dimensional cube. Again, here, okay, is this going to be the same as 1? And that's what we'll talk about next. So these are just some simple examples. Let me erase here. So here's a theorem that will help us. So before I say the theorem, again, this h of gamma, so some people give, you like to assign kind of informal meanings to various parameters. H of gamma measures how, if your graph has essentially bottlenecks. So a bottleneck is something that we saw here for Cn. So here for Cn, what we saw is that you can actually break the graph into half. You break it in two pieces, each of them of the half of the order, by deleting only two edges. So I could have done this picture a little bit differently. I could have drawn it like this, like you have these bottlenecks and you have this big graph that basically gets broken down into two pieces. So when you have h of gamma small, in this case is pretty much almost as small as it can be for connected graphs, what it means you have a bottleneck, which is you probably don't want this if you want to build some network with connectivity properties and so on. So the meaning of small h of gamma means the graph has a bottleneck. Large h of gamma, it means that the graph is highly connected. It means that in order for you, so let me write it here just before I give you the theorem, and then I'll write the theorem on the other side. So h of gamma small means gamma has at least a bottleneck. H of gamma large, we'll see in a second. This means gamma is highly connected. Highly connected. What I mean by it, in order to disconnect, so in order disconnect the graph, let's say into some parts like this, S and V minus S, let me call this T and V minus T. One has to delete many edges. So by many edges, what I mean is that because of this definition, h of gamma equals the minimum of value of this, what it means is that for any, let me use a different set, for any t in V with cardinality of t at most n over 2, the number of edges between t and V minus t has to be greater or equal than this parameter h of gamma times the cardinality of t. So for any t, if you want to break t away from the rest of the pack, you have to delete some kind of constant, linearly many edges, linearly in cardinality of t. Okay, you have to pay this price. So that's what I mean by highly connected. So if you want to break it into larger pieces, so let's say t is kind of linear in n third, you're gonna need to delete at least some constant times n third. If this is n half, the same thing. Okay. Okay, so let's write down now the theorem. If gamma is a connected deregular graph with eigenvalues, these are the eigenvalues of the adjacency matrix. D equals lambda 1, bigger than lambda 2, bigger than lambda n, then this expansion constant of gamma is bounded by below and above by two quantities which involve the gap here between d and lambda 2. So it's going to be less than or equal than square root of d square minus lambda 2 square, and it's going to be greater or equal than d minus lambda 2 over 2. Okay, so this theorem was done in the 80s by various authors. I won't give you all now the names, but so what this is saying, so this parameter is difficult for us to determine in general, and we saw that, you know, nobody wants to do 500 cases or anything like that. And you have the situation that for h of g, we can find upper bounds by picking sets and so on. It turns out you can find an upper bound in general by doing this upper bound, but you have this also lower bound. So what I'll show you now, I'll give you a proof of the lower bound, because we can do this with, you can do it in a different way with the Rayleigh quotient, but I'll do it with eigenvalue interlacing so that you can see an application of it. The proof here, it's a bit more complicated than, I won't do it here, but yeah, we won't need it for the rest of what we're doing today. Okay. So for example, just to show you a quick application of this, for Peterson, we agree the expansion constant is at most 1. Now, what is d minus, for Peterson, what is d minus lambda 2 over 2? D is 3, lambda 2 is 1 over 2, you get 1. So it means it has to be 1. So that's the easy proof that you can give. For the cubes, so this one, like I said, it works for every cube. HQ of n is always going to be at most 1. For the n-dimensional cube, the degree is n, and the second eigenvalue, we haven't done it, but I'll talk to you a bit about it in the afternoon, is n minus 2. So when you do this calculation, d minus lambda 2 over 2, you also get 1. So you can, okay. Okay, so let's do the proof. So I'll prove here. We want to prove that h of, let's put it like this, d minus lambda 2. Okay, so what you start with h of gamma. You want to look at it a little bit more carefully. So h of gamma, so I erase the definition, I'll write it again. So we have that it's this minimum over all subsets of S at most, let's say n over 2. So let me have n is cardinality of V. Okay? So here, the graph is finite, so this is a minimum. It's a finite set of things, so this is attained. So there is a subset S. They could be more, like you saw it here. They could be more subsets S. It's the inner 5 cycle, the outer 5 cycle, such that you have equality. So let's say let T be a subset of V such that, what do I want? Cardinality of T is at most n over 2, and if I look at the number of edges between T and V minus T and I divide by h of T, this is h of gamma. So I have some T here, and I have some V minus T, and I have some edges in between them. Okay? So I'll denote the cardinality of T by lowercase t. So what I'm interested in this quantity. Okay? So this is now, so I want to prove that h of gamma is greater or equal than d minus lambda 2. But h of gamma is this quantity. So I will prove that this quantity is greater than this. So now, it's a picture we've done a few times this week. You have a partition T and V minus T. Okay? You don't know anything about it, but you know the graph is deregular. So at the beginning, just write down what is the quotient matrix of the partition. We have done this a few times by now. So let's do that. Yes?
All the examples, like the minimum is identity from the set, which is exactly n by 2 number of.
Yes. It's not going to be the case. I don't think it's a case. It's not the case in general. This is just happened here. I'll think about an example, but it's not the case. Okay. So let me erase it. Okay, so the quotient matrix of this partition is the following B, and to make our life easier, let me give the number of edges between t and minus t. Let me t and v minus t. Let me give it a name. So let's call that E. E is the number of edges between t and v minus t. Okay. So again, I have this. I have this. I have E here. Here, cardinality of t is t. Here, cardinality of v minus t is n minus t. Okay, so in this case, we've done this before. Which ones are the entries that are the easiest to pick? Maybe the off-diagonal ones. The off-diagonal ones, because in the entry here, I want to calculate the number of edges in between divided by here. So this is going to be E over T. And in the entry here, you will get E over N minus T. And this is a D-regular graph, and we argued before the sum has to be D, so here it fills up by itself. This is D minus ET, and this is D minus E over N minus T. It's the same matrix that I did for edge connectivity. It's the same matrix. Okay, now we are going to look at something else. Okay, so as before, lambda 1 of B is D, and lambda 2 of B is going to be the trace of B minus D, and this will be D minus E over T minus E over N minus T, and I'll simplify this a little bit. It will be D minus the t and n minus t. When you bring to the common denominator, you will have a t n minus t here, but they add up to n, so it will be n times e. So at this point, I haven't done anything. It's just I did my homework to do the calculations for the quotient matrix, and now by Hammer's interlacing, what do we know? We know that lambda 2 of A, which I denote by lambda 2, is going to be greater or equal than lambda 2 of B, which is this thing. Okay, so here you just have to do small steps and kind of look at what we're trying to go after. We're trying to go after this H, and this H in our notation is exactly E over T. So you're trying to isolate that. So let's try to do that. Okay. Okay, so from here, I will move the fraction to the left-hand side, so I'll get NE over T, N minus T. I'll move it, and this is going to be greater or equal than D minus lambda 2. Everybody sees this? So I have an inequality. Lambda 2 is greater than here. I move the minus this, I'll move it to the left, and I move lambda 2 to the right. Okay? And now the interest for me is E over T, so I get rid of these things. So I get E over T is going to be greater or equal than D minus lambda 2 times N minus T divided by N. We're almost, you kind of, E over T, D minus lambda 2. There was something around D minus lambda 2. And we got here, but now the T was the cardinality of t. And what was special about it? At most n over 2. So if this is at most n over 2, then n minus t is at least n over 2. So that means n minus t over n is at least 1/2. Then this will be greater or equal than 1/2 d minus lambda 2. And actually, so this gives you the inequality of 1/2 d minus lambda 2. But you can also say a little bit more, coming back to the question that one of you asked earlier. So you have this, we proved this. When do you get equality? Equality will have equality there. If you have equality everything here, so t will have to be n over 2 and n will have to be even. Here you see if n is not even, if n is odd, then this becomes a strict inequality here. So you're not going to get equality. And then what else? So n has to be even. And then you have to have equality in the hammers interlacing. And that means that interlacing is tight, which means that this partition has to be equitable. And that's exactly the case both for the Peterson graph and for the cube. You saw like that partition is actually equitable. Okay, so that's the equality case. So this will happen rarely, but as you see, it will happen. Okay, so that's the proof. Again, it's not it's fairly simple, and like I said, you can give a different proof by using the Rayleigh quotient characterization of lambda 2. So let me just give you the idea here. So you can give a second proof. In some sense, these proofs are kind of related, if not equivalent, but so lambda 2 of the graph. So for the second proof, you can write it differently. You can say lambda 2 is the maximum over all vectors u in Rn, u which is perpendicular to the all-one vector of u transpose AU, u transpose u. Okay, so lambda 2 is the largest Rayleigh quotient of every vector which is in the orthogonal complement of the all-one vector. And then you pick a t such that t will give you the expansion constant, and from this t you define a vector v, which in terms of t. Okay, let me think if I can do it on the spot now. You want something that is perpendicular. You want something that is perpendicular on to 0. So let's say my entries in t are here. The entries in v minus t are here. So the easiest way, on the entries in t, I put n minus t, n minus t. Okay, I can put these numbers. In the entries in v minus t, I put minus t, minus t. And I do this so that this v is perpendicular to 1. Because if I take the inner product of this v with 1, what do I get? I get n minus t, you sum up n minus t how many times? T times minus t times n minus t, so it's 0. So you do this just so that v is perpendicular to 1. And then you take this v and you plug it into here, and you'll get essentially this kind of inequality that I got from here, something like this. Okay, so yeah, that works. But this is like if you know these things about the interlacing and so on, this is just I think it's easier to think about. Okay, all right. Okay, so I gave you something here. Let me write it. Now, for this, in this area, what are people interested in? So the big problem, the problem of interest, okay, you can put dollar signs on it if you want or something. It's a big problem. Is the following: given d greater or equal to 3, Find, construct a family, let me call it gamma m greater or equal to 1 of graphs, such that 1, gamma m, so is d-regular for each m, and the number of vertices in gamma m goes to infinity as m goes to infinity. So you want to find an infinite sequence of d-regular graph with number of vertices going large. That's, I show you one way to do it. But you need a second constant, second property, and there is some positive constant c, which can depend on d, will depend on d, positive, such that the expansion constant of every graph is at least this c for any. So what you want is that the expansion constants of these graphs to be bounded away from 0. So c, you have 0 here, you have c here. So this expansion constant, this hg of m, they're not getting anywhere near 0. Okay, so I'll show you in a second why I say d greater or equal to 3. But okay, so this is what is called the family of expanders. Okay, so you fix the d. So think about now for d equals 3, and you want a family of graphs, 3 regular graphs with 10, 100, 1,000, 1 million, 1 billion, okay, and so on vertices. That's here, such that these graphs, the expansion constant is bounded away from 0. Now, so there are two things that are in play here. So these graphs here, because I fixed the d and the number of vertices grows large, the number of edges in these graphs, the number of edges in any regular graph is the valency times the number of vertices divided by 2. So here, the number of edges in this graph will be d times the number of vertices divided by 2. But if d is fixed, then this number of edges is linear in the number of vertices, which for a connected graph is asymptotically as best as you can, because the tree will be linear, and that's the least you can have. Here, you're going to have more edges than in a tree, but for example, if d is 3, you will have 1.5 times the number of vertices in the graph. In a tree, you have number of vertices minus 1, but this is as good as you get for connectivity, for a graph being sparse as a regular graph. Now the second condition, so this first condition, like I said, it means that these graphs are sparse. So sparse means you don't have many edges. You have linear many edges in the number of vertices, which again, like I said, asymptotically is best possible for connected graphs. The second condition, there is C such that all these graphs has expansion constant bigger than 0. This is something that, if you think for a second, it feels almost impossible for it to be impossible for it to happen, because these graphs, think about it, you have a 3 regular graph on 1 billion vertices. It's connected, but it's a 3 regular graph on 1 billion, Even here, we have like 50, 60 people, and if we make a graph, 3 regular graph, you will feel like kind of sparse. But imagine, it's sparse, 3 regular on something on 1 billion vertices. So if the graph is so sparse, how in the world can it be so connected? Because you have this condition. So this C, it doesn't have to be 1 like we said before. It could be something 0.00000 something, but it's a positive constant that does not depend on the graph. That's the key thing. It's like I said, it may depend on the degree for general construction, but in general, it's something that separates all these expansion constants from 0, away from 0. Okay, so the first condition is sparse. The second condition means they're highly connected. So you will see it in various books. At the beginning of the introduction, people will just say expanders are sparse and highly connected graphs. But the way you should look at the question about expanders is that you're fixing the valency, constant degree, and you want an infinite family of graphs. Okay, so that's the general question. Eh? It is what?
Interested on connected graphs.
Yeah, connected graphs. So yeah. I mean, because of this h bigger than 0, they will have to be connected. Yeah, let's say connected. Yeah. But this ensures if your expansion is bounded away from 0, you must be connected. Because if you're disconnected, your expansion is 0. Okay. Yeah. Questions? Yes.
Sparse is this only this graph of the family of the graph?
I mean, that's a very good question. So the sparse will apply pretty much to, again, you can think of it, so you have this family, and you can think of them, all of them being, they will be sparse.
Actually, I want to know the intuition of the meaning of the sparse.
So meaning of the sparse is, again, if I look at the number of edges in such a graph, gamma m, this will be d times the number of vertices in gamma m divided by 2, okay? So this is linear in the number of vertices of gamma m because because d is fixed. So d doesn't change with the gamma m. So d, like I said, pick for example 3. So if you pick d equals 3, so for d equals 3, the number of edges in your graph will be 1.5 times the number of vertices in gamma m. And again, we're looking at it asymptotically as a connected graph. What's the smallest number of edges you can have? It's a tree, in a tree. So that would be number of vertices of gamma minus 1. But this is linear in number of vertices. This is also linear in number of vertices. So that's what I mean by sparse. For these d-regular graphs, this is the least number of edges that you'll be able to have. Okay, so that's the meaning of sparse. So the degree being fixed and the number of vertices going large. Again, like I said, think about a graph a connected graph with 1 billion vertices in which every vertex has 3 neighbors. That's sparse. Okay. So yeah, so that's this meaning here of sparse. Highly connected, h of gamma is bigger than c. So basically, each of these graphs does not have, it's highly connected. Like if you want to break this graph into 2 large parts, you have to delete at least c times the cardinality of the smaller part number of edges. And this c, I'll give you an example. This c it does not depend on the graph. This c is kind of like an absolute barrier away from 0 from each of these expansions. Okay. Okay. Yes.
Other direction.
Eh?
What is used in the proof of the other direction?
In the proof of the other direction, what you do is so you take an eigenvector which corresponds to the second largest eigenvalue, and you kind of split your vertices according to something about the entries in the eigenvector in some kind of levels, and you use the fact that this expansion constant will tell you what's a lower bound on the number of edges between 2 parts, if they're okay. So it's more intricate. I think it's a proof that comes from geometry and analysis, where people have proved something like that. It's something called Chigger constant in general. So I'll show you, but that proof will take me probably an hour or so to do it. So I don't want to do it here. Okay. But you see, okay, so this is what people want, and now let me write it here. The problem from here becomes the following: because you have this this inequality of expansion constant being between these things and these things. So this is, let's say, problem 1, this is problem 2. It's the same thing as before, given d greater or equal to, find, construct family of connected graphs such that the first condition stays the same, so gamma m is d-regular for any m. So the sparse is the same here, the same here. But now this highly connected condition, which is here in terms of the expansion constant, here gets replaced by an eigenvalue constant. There is some constant, let's call it C prime, which again can depend on D, which is positive, such that D minus lambda 2 of every of these gamma m is greater or equal than C prime for any m greater or equal to 1. So the first condition stays the same. You want d-regular graphs for any m, so the same thing is the sparse condition, okay? But the second condition, here it says I want this expansion constant to be bounded away from 0. Expansion constant is difficult to calculate in general. Here, this is just some lucky coincidences for small graphs, you can do it, but in general it's difficult. But the expansion constant is bounded away from these two things. So what we say is that these expansion constants are bounded away from 0 if and only if the spectral gap d minus lambda 2 is bounded away from 0. So how do you see that? Well, if d minus lambda 2 is let me put it is bigger than some constant, let's say like here C prime, then I use the left hand side of the inequality, and I get h of gamma greater than C prime over 2, so I can take this C prime over 2 to be C. Okay, it's positive. The other way around, if h of gamma is bigger than C, then I use this other inequality from here, and I have square root of d squared minus lambda squared greater than C. But this number here, what is it? I'll erase here. But you have square root of d squared minus lambda squared. It's bigger than C. But on the other hand, this is square root of d plus lambda 2 times d minus lambda 2, and it's strictly less than square root of 2d times d minus lambda 2. So now if you take these two things, you get 2d times d minus lambda 2 bigger than c squared, which implies d minus lambda 2 is bigger than c squared over 2d, and you can take this to be your constant c prime to be bigger than 0. Okay? So the problem, you change the problem from here because this is something hard to deal with. You change it to something about d minus lambda 2. And now the question becomes a question about eigenvalues. Fix the d, construct an infinite family of d-regular graphs such that d minus lambda 2 is bounded away from 0. Okay, and this is, again, kind of the essential question in this area. This is the big question, okay? All right. Now, before I tell you more about this, so we look at this, we leave problem 1 aside and we'll look at problem 2. Let me tell you one quick thing about why did we take d greater or equal to 3. What happened to d equals 2? Well, for d equals 2, what are the only d-regular connected graphs? Cycles. So if you have cycles, Cn, what did we see earlier? H of cycle Cn which say it's about 4 by n. What happens to this as n goes large? Can you keep it away from 0? You can't. So for d equals 2, you know, you cannot do any, there's no way you can make any infinite family of expanders. Okay, because the cycles are not expanders. Cycles are sparse, but they have bottlenecks. You have 2 edges in the middle, you delete it, you broke the graph in half, and you're done. Okay, so that's the simple thing. Okay. So now you come back to this problem and you change the problem again, because you see d is fixed. D is fixed. You want d minus lambda 2 to be bounded away from 0, so you want it maybe to make it as large as possible. But d is fixed, so it means you want lambda 2 to be as small as possible. Okay? And the question is, okay, what, you know, how small can you make lambda 2? What's the what can you do about lambda 2? Well, so this is what we want. Okay, this is the goal, or what people want. And now let's see what the reality is. What do graphs? What is nature? You know, what is the nature of the graphs? So here's the following result. So this is a theorem. The first part, this one is a theorem which is called Alon-Boppana theorem from 1980s. Alon and Boppana wrote many papers. The theorem that I'll give you is in none of those papers. Okay, it's in another paper written by Alon, and it says the following: if gamma is a d-regular graph with again d-regular connected graph with n vertices and let's say diameter d, then lambda 2 of gamma, what it does, it's greater or equal than 2 square root of d minus 1 minus some constant. Let me do c double prime, not the other constants, divided by the diameter. Now, what this expression will be, this expression is the same thing as a 2 square root of d minus 1 minus some quantity, I'll call it little o of 1, where this little o of 1 goes to 0 as the diameter goes large, or as the number of vertices grow large. Okay, and so this Alon-Boppana theorem has a consequence which I like to call the an asymptotic Alon-Boppana theorem, and I'll explain in a second the connection. And it says that if you have a sequence as before is a sequence of connected d-regular graphs with a number of vertices going to infinity as m goes to infinity, then if you look at the second eigenvalue of these graphs, lambda 2 of gamma n, you may not have a limit of them, but you will always have a lim-inf as n goes to as m goes to infinity. This is at least 2 square root of d minus 1. So what happens is, what the second part says is that if you have a sequence of d-regular graphs, a constant degree d-regular graphs, with a number of vertices going to infinity, the natural behavior of these graphs, of the second eigenvalue of this graph, is to become greater or equal than 2 square root of d minus 1. I haven't told you about 2 square root of d minus 1, but it appeared kind of out of the blue, but maybe I'll give you a presentation a little bit about it. But that is the natural behavior of this. So on this problem, you want d minus lambda 2 as large as possible. You want lambda 2 as small as possible. You want to keep lambda 2 somewhere, we want to, so for this problem, you have 0 here, and you want to put something here, and you want to keep all the lambda 2's in gamma. Here is d, here there's d, and then you want to put some kind of barrier, and you want to keep all the lambda 2 of gamma in here, okay? Now, this problem, what it tells you is that you have d here, you have 0, and then you have some number here, 2 square root of d minus 1, and all these lambda 2's, what they're trying to do is they're trying to get out. Okay, greater or equal, limit, okay? Okay. So, now, there is another theorem, which is a theorem due to Serre, and I'll just state it here. Don't know if I'll have time to prove it, which is kind of tells you even more, and this is a theorem of Serre from 1990s, mid-1990s. What it says, Serre's theorem is going to say that it's not just the second eigenvalue of these graphs that tries to become greater or equal than 2 square root of d minus 1. It is a positive chunk of the spectrum of these graphs that's trying to escape through there. So the way I will phrase it is as following. For any d greater or equal to 3 and any epsilon positive, there is a constant C double triple prime, okay, which depends on d and epsilon, which is positive, such that give me just a second if I need n sufficiently large. Yeah, no, I don't need. So there is a positive constant such that any d regular graph on n vertices has at least this C triple prime times n eigenvalues greater than or equal to two square root of d minus 1 minus epsilon. Okay, so what does it mean? You give me any d, let's take 3. You give me any epsilon, so essentially what we're doing is you have a d here, you have the 0 here, you have the 2 square root of d minus 1, and you're giving yourself a little bit of room here. This is 2 square root of d minus 1 minus epsilon. Okay? So you move a little bit left from t to 2 square root of d minus 1. So what it says is that any d regular graph you give me on n vertices, you will have at least this many. So this is a positive constant. It does not depend on n. It depends only on d and epsilon. Such that this graph will have at least, so in general, how many, well, in general, always, how many eigenvalues does the graph have? N. And this C prime, C triple prime, can you imagine is a number between 0 and 1, and it can be like exponentially small, but it depends only on d and epsilon. And you think of d and epsilon fixed, and you think of n and large, although this works for any n. So every graph will contain a positive proportion of its spectrum that is trying to go above. Okay, so not just the second eigenvalue, it will be like a big chunk. So this theorem, like this, What's your favorite number? 31. Today is October 31, okay? If you can put here lambda of 31 of this graph, this will try to become bigger than 2 square root of d minus 1. Okay, so that's so the behavior of the graph is that somehow these 2 square root of d minus 1, they all try to escape through there. Yeah, so on one hand, these graphs, you want to keep lambda 2 small. On the other hand, you want to keep lambda 2 tries to become bigger than equal than 2 square root of d minus 1. So now, okay, so what happens? Well, here's what happens. So this is something I think all of you should know about, is that definition, connected d-regular graph gamma with eigenvalues d bigger than lambda 2 bigger or equal to lambda n is called Ramanujan if lambda 2 is less than or equal than 2 square root of d minus 1. So Ramanujan graphs are the graphs in which you can keep everything lambda 2, you can keep lambda 2 in a fence, and the fence is a 2 square root of d minus 1, which by this theorem is best possible. You cannot move the fence anywhere to the left, okay? Now, Ramanujan, as you all know, did many things. This is not his definition. So this was a definition that was introduced in a paper by Lubotsky, Phillips, and Sarnak. They have a paper called Ramanujan Graphs in 1988 in Combinatorica. And the reason is that in the same paper, they give a construction of family of d-regular Ramanujan graphs for d equals a prime plus 1, p plus 1, p prime. So this construction is an amazing construction. These graphs are Cayley graphs of some matrix groups, and in showing that the graphs are Ramanujan, what they use results from number theory related to a conjecture of Ramanujan about the number of ways of writing a natural number is the sum of 4 squares of a certain kind. So for this one, I highly recommend. The paper is very well written. You can do that, but let's say maybe you don't remember some things from number theory. When is a number of sum of 2 squares? When is a number of sum of 4 squares? And stuff like that. There is a beautiful book that was written by Davidov, Valette, and Sarnak. I think it's something called Elementary Number Theory, Group Theory, and Ramanujan Graphs, and it gives like a self-contained presentation and proof of this paper. So it starts with number theory, proves all the results. It starts with spectral graph theory, proves some of these results that we did here, and then it gives you the construction. So this is, I highly recommend it if you're interested in finding out. It's a beautiful proof. Okay. All right. So for the longest time, so that was the status. So many people are looking for families of d-regular Ramanujan graphs. This construction uses again tools from number theory and algebra and so on. It was extended later on by Morgenstern to d equals a prime power plus 1, also like a complicated algebraic construction. And people are asking, okay, what happens for for any, for other degrees, what's the situation. So let me tell you what happens for other degrees, so because it will tie in a little bit with this notion of two cover that we talked about. So the idea that the idea of using two covers to construct like infinite families, this it appears in a paper by Bilou and Lineal, I think 2006. So Lineal has a sequence of papers in which he studies two covers and various properties of two covers in terms of the basic graphs. But here they wanted to show that two covers, they wanted to start with a graph, show that there is a two cover that where the eigenvalues are bounded and repeat and so on. So they prove something that any d-regular graph has a two cover with eigenvalues at most something like a constant, I think d to the, I forget how, let me see, I may have it here. Yeah, it was square root of d log 3d, something like that, for some C4 triple, C4, some C4 positive. So if you have this theorem, then you can construct an infinite family of d-regular graphs where the second eigenvalue is at most this much by doing the recipe that I told you. You start off with a complete graph kd plus 1. This is actually Ramanujan. Then you do find a two cover like this, bigger graph, and then find a two cover, and everything is bounded. Now, before I tell you more, sorry, I have to go back here really quick. So some people call this Ramanujan lambda 2, or the other definition that you will have for Ramanujan so the other people use a different definition, which is not just second eigenvalue, but the whole spectrum. Absolute value of lambda j is at most 2 square root of d minus 1 for every j greater or equal to 2. So the difference between them is that here you just bound the right side of the spectrum. Here you bound the whole. So here you have d, you have 2 root d minus 1. You have minus 2 root d minus 1, and all your spectrum are in here. Okay, so you have this. Here you have d, you have 2 root d minus 1, and then here you could have minus d, and so on, and you only care about here, lambda 2 being there. Here you could be close to minus d. Okay, so clearly this one implies this one, but not vice versa. Okay, so there are two definitions. Yes?
So did they construct a family for each prime number p, or?
Yes.
Okay.
So you fix the p, then the degree will be p plus 1, and they find an infinite family of these graphs. Okay, so that's the approach with like I said, with algebra and number theory, and there are other approaches like that. This one is different. So Bilou and Lineal said, okay, how do I find a sequence of d-regular graphs? Take these covers, and they prove this general theorem. Any d-regular graph has a cover with eigenvalues at most some positive constant square root of d. You see here, it's not quite the bound of that you want for a Ramanujan graph, 2 square root of d minus 1, but that's good enough. And they find this infinite, they show this existence of infinite family of expanders. And then later on, this work was extended by Marcus, Spielmann, and Srivastava. I think this is 2014, 15, something like that. And they proved something of the following: any d-regular graph, connected graph has a 2 cover with the new eigenvalue, so lambda 2 of the adjacency matrix with all the eigenvalues. So here, with all eigenvalues at most 2 square root of d minus 1. So by this recipe, you can show there is an infinite family of d-regular Ramanujan graphs, like Ramanujan graphs in that sense with lambda 2 at most 2 square root of d minus 1. So they could control just the top part of they couldn't control, I mean, you can control the bottom part of the spectrum, but then you cannot control the top part of the spectrum. So they couldn't control both of them at the same time. And their result is based on this idea. You know, like, I mean, this obviously it's the same concept for any you know, you start with something that is Ramanujan, there is a 2 cover like this, you take that 2 cover, then you take there's a 2 cover of the 2 cover which has the property that you want, and you repeat. Okay. Now here, let me give you an idea about how they did this, and I will finish. So their idea is the following. So here, what you have to control is you look at these sign adjacency matrices, because that's where the new, yes?
All groups are from bipartite.
No, they have something for bipartite too, but this is for all d-regular graphs. So let me, okay, this is 2. Here they proved, so a consequence of this is that for any d, there is a family of bipartite d-regular graphs where not just where absolute value of lambda j is at most 2 square root of d minus 1 for any lambda j that is not plus or minus d. So, but this theorem is true for any graph. But so they use a definition with absolute value so they use this definition for Ramanujan graphs. So if you use this and you want a Ramanujan graph, you cannot get them with the first property. But if you start with a bipartite graph, what happens on the positive side happens on the negative side in reflected, and that's how they do it. Okay. So just one more minute and then I'll stop. There are many, yes?
Value in the first one.
Yeah, with all, yeah. Or all eigenvalues. Yeah, lambda 2 is a most, yeah. So there are many beautiful things in this paper, and it is a very well written paper, so I highly recommend it to read it yourself. You can find it online. What they did is, okay, this graph, when you do a 2 cover, you have the old eigenvalues. You can take a graph so that old eigenvalues are what you want, are nice, are small. So the game is about all these sign adjacency matrices. Okay, so people ask questions. Okay, what can we say about it, and so on. There is a result of Gotzil and Gutmann from the 80s that says that the average of the characteristic polynomials of this sign matrices S, as you run over all 2 to the number of edges signed adjacency matrix, equals something called the matching polynomial of gamma. So this is a polynomial of degree number of vertices where the coefficients alternate in sign, and they count in absolute value. They count the number of matchings of various sizes. I'm not going to go through it. It's another another Gian course about matching polynomial. Then what happens is this matching polynomial of gamma, it is known from like 70s from some physicians, Hallman and Lieb, but if you want actually nice proof, you can go into Gotzel's book, Algebraic Combinatorics, where he proves this this thing is that the matching polynomial of a graph, of any graph, has real roots, but the matching polynomial of a d-regular graph has real roots that are all at most 2 square root of d minus 1. So you want this characteristic polynomial to have all the roots at most 2 square root of d minus 1. You don't know how to pick such a polynomial. So what you do, you average all of them. You think that is crazy, but this was done before, so people average this, and you get the matching polynomial. That's already done. It was already known that the matching polynomial has real roots, which are all at most 2 square root of d minus 1. So here, this is the magic stuff that Marcus Spielmann and Srivastava did, and they introduced something called interlacing polynomials. And in general, just because some polynomials average a polynomial, and that polynomial, which is the average, has an eigenvalue at most 5, doesn't mean that one of your polynomials has a root at most 5. It doesn't work like with numbers. But they proved that so this is their big contribution here, and they proved that there will be a polynomial from here that has all the roots at most 2 square root of d minus 1. Just because from these two. So that's the idea. So again, the basic idea is like at the base of it is this notion of 2 cover and sign adjacency matrices, and in general, it's difficult to pick. Okay, give me a signing such that this happens. That's going to be difficult, but something like an average, people know what it is, and they've done amazing things with it. Okay. All right, so I'll stop here. Sorry, it's time for coffee. Thank you.